All right, in this video, we will be going over section 2.5. In this section, we will be talking about derivatives of exponential and logarithmic functions. All right, I want to start with this theorem 2.13, derivatives of exponential functions. Okay, here is the statement of the theorem. For any constant k, any constant b greater than 0 with b is not equal to 0, and for all x in R, we have this differentiation formula. The derivative of e to the power x is e to the power x itself. Okay, d over dx e to the power x means the derivative of e to the power x. Okay, that's how you denote the derivative of e to the power x. So the derivative of e to the power x is e to the power x itself, and then the derivative of b to the power x is ln b times b to the power x. In part C, the derivative of e to the power kx is k times e to the power kx. Okay, you can think of this is like k is walking to the front, and then this term stays as it is, k times e to the power kx. All right, I want to prove some of these formulas. Let's prove the first two derivative formulas, and then I will leave the last one as an exercise. Okay, so how do we prove the derivative of e to the power x is e to the power x itself? Well, I'm going to take f of x to be e to the power x. Okay, then I want to show that f prime of x is again e to the power x. Okay, f prime of x is also e to the power x. That's what I want to show. Okay, how do you show that the derivative of this function is e to the power x? Well, I'm using the definition of the derivative. By definition, the derivative is going to be limit h approaches to 0, f of x plus h minus f of x divided by h, right? Now I can find f of x plus h, limit as h approaches to 0, f of x plus h is e to the power x plus h. You just plug in x plus h in the function f of x, minus f of x divided by h. Oh, by the way, this f of x is nothing but, this f of x is nothing but e to the power x. I can put e to the power x here. Now what I'm going to do is, I'm going to write e to the power x plus h as e to the power x times e to the power h minus e to the power x divided by h. You know, by exponent rules that you learn in your pre-calculus class, these two are the same. Okay. All right. Now I'm going to pull out e to the power x from the top. Limit as h approaches to 0. If I pull out e to the power x, you get e to the power h minus 1 divided by h. That's what you get. Okay. Now notice that I'm taking the limit as h approaches to 0. It has nothing to do with e to the power x. E to the power x looks like a constant as h approaches to 0. So this works out. So this is equal to e to the power x times limit as h approaches to 0, e to the power h minus 1 divided by h. But we know by theorem 1.26, this limit is equal to 1. Okay, e to the power x times 1. This is by theorem 1.26. By theorem 1.26. Okay, so we have e to the power x times 1, which is e to the power x. So that means we have proven that the derivative of f of x, f prime of x, is equal to e to the power x. That's what we wanted to prove. Derivative of e to the power x is e to the power x itself. Okay, now I want to show you some additional thing here. That is, how would you find, now we know that if we have e to the power x, the derivative of e to the power x is also e to the power x. Now what if you have y is equal to e to the power a star? Star means some complicated expression. Your power is a complicated expression. How do you take the derivative of this one? Well, you are going to have to use the chain rule, right? Chain rule or the star rule that we talked about in section 2.4. So how do you apply the star rule here to take the derivative of this function? What you do is you pretend like you have x here. If you had x here, you know how to differentiate that. If you have just x here, the derivative of this function is e to the power x itself. You just pretend like you have x here. If you had x here, the derivative would be y prime of y prime is equal to e to the power star. But you are not done yet because this is not x. If you have x here, the derivative of e to the power x is e to the power x itself. So I follow a similar pattern here. The derivative of e to the power star is e to the power star itself times the derivative of your star. D over dx times d over dx your star, the derivative of your star. Okay, that's the derivative formula or the chain rule. When you have a power other than x, of course, if this power is x, you know how to take the derivative. That is, the derivative of e to the power x is e to the power x itself. But if you have a star here, the derivative of this function is e to the power star times the derivative of the star. That is d over dx your star. Okay, that's the formula that we'll be using. This is nothing but the chain rule. Okay, this is none other than your chain rule. Okay, so keeping that in mind, let's prove the second part. I will copy this star rule for e to the power x to the other side. Next, I want to prove the second part of that theorem. I'll copy my star rule over here. Okay, so let's see. Here is the second part. The derivative of b to the power x is ln b times b to the power x. How do we prove this? Well, so at the end of the day, I'm supposed to find d over dx b to the power x, right? The derivative of b to the power x. I'm going to rewrite this b this way. B is same as e to the power ln b. Okay, you learn this in your pre-calculus class, because we know that if you take g of x to be e to the power x, and g inverse of x would be ln x. Or in other words, e to the power x and ln x are inverses of each other. So that means e to the power ln b is nothing but just b. Okay, so I'm replacing my b by e to the power ln b. They are the same. Okay, this thing is b. So now what I'm going to do is, you have a power here, e to the power this thing, and to the power x. So using the power rule that exponent rules that you learned in your pre-calculus class, I can multiply those two powers. This will be e to the power x times ln b. You just multiply this and these two numbers. Okay, that is one of the exponent rules that you learn in your pre-calculus class. Now, how do I handle this? Can I take the derivative of this one now? Can I take the derivative of this function? Well, of course, yes, because see, as you can see here, you have e to the power some complicated expression. Okay, so you can view this complicated expression as your star. So you know how to differentiate e to the power star. The derivative of e to the power star would be e to the power star times the derivative of the star. Okay, e to the power star times the derivative of the star. So let's apply that star rule here. This is going to be equal to e to the power that thing times x times ln b times the derivative of the star. Your star is this expression. What is the derivative of this expression? Notice that ln b is a constant. So this is constant times x. So you leave this constant as it is and take the derivative of this piece. Derivative of x is 1. So that is just ln b. Or in other words, the derivative of x times ln b is just ln b. All right, I can do a little bit of simplification here. Notice that here, you have this x in front. I can send this x as the power here. That is one of the logarithmic rules. If you look at this rule, if you have r times ln x, that is same thing as ln x to the power r. So I can send this power x here. This is equal to e to the power ln b to the power x times ln b. Now notice that, what is this? This is just b to the power x, because this is e to the power ln bx. Okay. If you want, you can write this within parentheses. Okay, you have e to the power ln bx. We know that e to the power x and ln of x are inverses of each other. So e to the power ln bx is same as just b to the power x. E to the power ln b to the power x is same as just b to the power x times ln b. Of course, I can write this ln b first. Because it's a multiplication, I can switch terms around. Ln b times b to the power x. That's what we wanted to prove. Okay, so the derivative of b to the power x is ln b times b to the power x. We are done. Okay, let's move on. Okay, next we have this interesting theorem, Theorem 2.14, rates of change and exponential functions. F prime of x is equal to k times f of x for some constant k, if and only if f is an exponential function of the form f of x is equal to a times e to the power kx. Okay, what this theorem tells you is that if the derivative of a function is a constant multiple of the original function, then your original function should be of the form a times e to the power kx. On the other hand, if your original function is of the form f of x is equal to a times e to the power kx, then the derivative of that function should be k times f of x. Okay, so this is an interesting theorem in this section. We are not going to prove this theorem, by the way. This is an interesting property of exponential function. All right, the next theorem that I want to talk about is the derivatives of logarithmic functions. This is theorem 2.15. Here is the statement of the theorem. For any constant b greater than 0 with b is not equal to 0 and all appropriate values of x, we have these derivative formulas. The derivative of log base bx is 1 over log b times x. And then the derivative of ln x is just 1 over x. And the derivative of ln of absolute value of x is again 1 over x. Notice that these derivatives are both the same. The derivative of ln of x and the derivative of ln of absolute value of x, they are the same. Okay, so I want to prove again some of the formula here. I will prove the second part and I will leave the other parts as an exercise. Okay, so how do you prove the first part, second part, pardon me. So here is how I'm going to prove it. I'm going to start with a statement like this. E to the power ln x is equal to x, because we know that, again, if you recall the previous argument, e to the power x and ln x, they are inverses of each other. That means e to the power ln x is same as just x, because e to the power x and ln x's are, they are inverses of each other. So I have this statement here, e to the power ln x is same as x. Now what I'm going to do is I'm going to take the derivative of both sides of this equation with respect to x. Okay, before I take the derivative, let me copy this star formula for e to the power x. that will help you to find the derivative there. Here is my star formula. Okay. Okay, how do I take the derivative of my left-hand side now? Well, as you can see, here you have e to the power star, right? It is not x. You have some complicated expression. That means you have e to the power star. Okay. So if you have a star, how do you differentiate that? Here is the star rule. If you have a star, the derivative of e to the power star would be e to the power star times the derivative of the star. So let's apply that rule here. The derivative of the left-hand side becomes e to the power star times the derivative of the star. D over dx ln x. That is the derivative of the star. Derivative of this expression is d over dx ln x. And what is the derivative of the right-hand side? Clearly it's 1, right? The derivative of x is 1. Now I'm going to isolate this one. Derivative of ln x, d over dx ln x is equal to 1 divided by e to the power ln x. But I know that e to the power ln x is just x. E to the power ln x is x. So I can replace this by x. Okay, I get the desired function. So the derivative of ln x, that means d over dx ln x is equal to 1 over x. That's what I wanted to prove. Okay, that proves that result. Okay, actually, let me prove the first part as well now. Real quick. Perhaps I will copy the first part to the other side. Let's see if we can quickly prove this. Okay, so what I'm going to do is, I want to show that the derivative of this function is 1 over ln b times x. So I'll take y is equal to log base b x. Then by definition of logarithm, this is equal to b to the power y is equal to x. This is by your pre-calculus, okay? From your pre-calculus, pre-calc. It's just the definition of logarithm, okay? This base comes to the other side. B to the power y is equal to x. Now what I'm going to do is, I'm going to take the logarithm of both sides. ln b to the power y, absolute value of that is equal to ln absolute value of x. Why do I take absolute value? That's because I don't know whether this x is positive or negative. Okay, if this x is negative, you cannot take ln. Okay, so that's why I'm taking the absolute value. Now, what I'm going to do is, I'm going to pull this power to the front. That is one of the logarithmic rules that I showed you earlier. In this formula, if you have r ln x, that is equal to ln x to the power r. Okay, so you can pull this r to the front. So if I do that here, this is what you get. Y times ln b, but you don't have to put the absolute value because I'm assuming that my b is positive. So I'm not going to put the absolute value here. ln b, y times ln b is equal to ln absolute value of x. Now I'm ready to take the derivative of both sides with respect to x. Notice that this is a constant. You have just y in front. The derivative of the left-hand side would be just y prime, because the derivative of y with respect to x is y prime, or dy over dx, times ln b is equal to, we know that the derivative of ln x is ln absolute value of x is 1 over x, the last formula. Okay, derivative of absolute value of x is just 1 over x. Okay. By the way, I did not prove that the derivative of this function is 1 over x, but in a similar argument that we used over here, you can show that the derivative of ln of absolute value of x is also going to be 1 over x. Okay. Basically, you consider two cases, when x is positive and when x is negative, and then you apply this to show that the derivative of ln of absolute value of x is 1 over x. I'm using that here. Okay. So the derivative of ln of absolute value of x is 1 over x. Now I can isolate my y prime. Y prime is equal to 1 over ln b times x. That's what I wanted to prove. The derivative of I took this as my y. Okay, I took that as my y. I showed that y prime is equal to this expression. That means the derivative of this expression is equal to this expression. That's what I wanted to establish. All right, let's move on. Yeah, actually, before I move on, here also I want to introduce a star formula, okay, or the chain rule. Now you know, if you have y is equal to ln x, you know how to take the derivative of this one. Y prime is equal to 1 over x, no problem. But what if you have y is equal to ln, in place of x, you have a star this time. How do you handle this one? How do you take the derivative of that one? Again, remember, star means some complicated expression other than x. So how do you take the derivative of this one? Well, you pretend like this is your x, and then you apply your basic rule. The derivative should be 1 over x. That means y prime here should be 1 over star. But you are not done yet because you didn't have x here. If you have x here, yes, you are done. 1 over x, you are done, but you have a star here. In that case, you have to write 1 over star times you need to pay the penalty. Penalty is that you multiply this by the derivative of your star. That is the star formula, okay, or the chain rule. Simply, it is the chain rule. Okay, we will be using this. All right, let's move on. The next thing I want to prove is this a formula for derivatives of inverse functions. All right, here is the statement. This is actually theorem 2.16 in the book. If f and f inverse are inverse functions and are both differentiable, then for all appropriate values of x, we have the derivative of f prime is equal to 1 over f prime of f inverse of x. Okay, so this is the formula. This is how you differentiate an inverse function. You can use this formula to differentiate an inverse function, inverse of a function. Okay, so let's prove this formula real quick. How do you prove this formula? Well, to prove this formula, I'm going to use a well-known identity, an identity about inverse functions. We know that f of f inverse of x is equal to x, right? From your pre-calculus class. If you take the composition of f inverse and f, it should give you the identity function. Okay, this is something that you learn in your pre-calculus class. Okay, now what I'm going to do is I'm going to differentiate both sides with respect to x. Okay, if I differentiate my left-hand side with respect to x, by chain rule, we get f prime of f inverse of x times the derivative of f inverse of x by chain rule. D over dx f inverse x is equal to the derivative of the right hand side is just 1. Okay, so now what I'm going to do is, this is what I was looking for. This is exactly this. So I'm going to isolate that. D over dx, this is by chain rule, okay? D over dx f inverse x is equal to 1 over f prime of f inverse of x. That establishes the formula. Okay, again, here to find the derivative of this expression, I apply the chain rule. Okay, so think of this as your star. You know how to take the derivative of f of x, right? The derivative of f of x is f prime of x. But here the problem is, what if you have a star here in place of x? In that case, the derivative would be f prime of the star times the derivative of the star. That's what I have exactly here. View this as your star. So you should have f prime of the star times the derivative of your star. I'm just applying the chain rule here. Okay, that will give you this formula as needed. All right, let's move on and let's work on some examples now. Okay, so here are the examples that I want to work on. Find the derivatives of each of the following functions. Here is the first function given to us. Let's try to find the derivative of this function. Okay, to find the derivative of this function, notice that we have a product of two functions, e to the power x cubed times ln of x. So I will take this function to be f of x and this function to be ln of x. Okay. And then I apply the product rule to find the derivative. Product rule is given here. Here is the product. Okay, if you have f times g, the derivative of that would be f prime of x times g of x plus f of x times g prime of x. Let's apply the product rule there. Then you get f prime of x is equal to, you need to take the derivative of this one first. How do you take the derivative of e to the power x cubed? Well, you use the star rule. If you have e to the power x, e to the power star, how do you take the derivative of that? The derivative of e to the power star is equal to e to the power star times the derivative of the star. Okay, so let's apply that here. Notice that in this case, your star is x cubed. So the derivative would be e to the power x cubed times the derivative of x cubed, d over dx x cubed. And don't forget you have ln x. That is, you took the derivative of this function and left this one fixed. Okay, and then plus, then you should have f of x times g prime of x. So you leave f of x fixed this time, e to the power x to the power 3 fixed, and then take the derivative of ln x. We know that the derivative of ln x is 1 over x from the previous formula. Okay. Now you can write one more line here, e to the power x to the power 3. You can take the derivative of x cubed, which is 3x squared, times ln x plus e to the x cubed divided by x. This is your answer. Okay. All right. Let's move on to the next example, which is a little complicated one. Here is the second part. I copied that to the other page. How do you take the derivative of this function? This divided by this. Well, again, here we need to apply a formula that we learned in a previous section. That is the quotient formula, right? You have division of two functions. So we are going to go with the quotient formula initially. Okay. So let's apply the quotient formula to find the derivative of this function. F prime of x is equal to, you should have log base 2x, that is your g of x. G of x squared should be in the bottom, as you can see in this formula. Okay, so I have that, and then let's get our top. What should I have in the top? Well, you should have f prime of x times g of x. F prime of x. F prime of x means you need to take the derivative of your top. How do you take the derivative of the top? That means the derivative of this plus derivative of this. Okay, so let's take the derivative of this. Derivative of e to the power 5x is e to the power 5x times the derivative of 5x, which is 5. I'm applying the star rule here. See, you have e to the power star. If you have e to the power star, the derivative of e to the power star is e to the power star times the derivative of the star. So I have e to the power star times the derivative of the star. Derivative of the star is just 5. And then I need to take the derivative of this piece. How do I take the derivative of this piece? There, we have to apply the product rule, right? Because this is a product of two functions. So let's apply the product rule there. Plus, I differentiate x to the power 3, which is 3x squared, and leave 2 to the power x fixed. Leave 2 to the power x fixed. And then plus, I leave x to the power 3 fixed and differentiate 2 to the power x. How do you differentiate 2 to the power x? Well, we can use this formula. The derivative of b to the power x is ln b times b to the power x. So the derivative of 2 to the power x should be, according to that formula, ln 2 times 2 to the power x. If you want, you can put this within parentheses. That would be the derivative of 2 to the power x would be ln 2 times 2 to the power x. Done. So we have the derivative of this piece completely. That is this piece. And don't forget, now we are applying the quotient rule. So this is parentheses. And then you need to have g of x here. That is log base 2x. Remember, in the formula, you need to have f prime of x times g of x. This whole thing is your f prime of x, and this is your g of x. And then minus f of x times g prime of x. F of x is this quantity, e to the power 5x plus x cubed times 2 to the power x times the derivative of g prime of x. That means the derivative of this function. How do you take the derivative of this function? Well, again, we have a formula. Derivative of log base b x is equal to 1 over ln b times x. So according to that formula, the derivative of this function would be, your b looks like 2, right? Here, so you plug in 2. So that will give you 1 over ln 2 times x. If you want, you can put parentheses here. So that will be the derivative. This whole thing, whole expression is the derivative of the given function. Okay. All right, that completes that example. Let's move on. Okay, next, let's look at this example, last part of the example. How do you take the derivative of this function? Well, again, you are going to have to use the star rule, right? Or the chain rule. So here is how you take the derivative of ln of star. The derivative of ln of star is 1 over star times the derivative of the star. D over dx, star means the derivative of the star. So let's apply that rule here. As you can see, you have a star here. You have a complicated expression inside logarithm. That means that's going to be your star. So let's apply the star rule. Your f prime of x will be 1 over star. Star is that complicated expression, divided by 3x minus 1 squared times the derivative of your star. D over dx, your star. Your star is, of course, 1 plus x squared divided by 3x minus 1 whole thing squared. Okay, so are we done now? We are not done yet because we need to find the derivative of this expression. Okay, let's try to find the derivative of this expression. Again, to find the derivative of this expression, I'm going to use the star rule or the chain rule. As you can see, this is a power, right? This thing to the power 2. But you know how to differentiate. If you had x here, you know how to differentiate x to the power 2, right? That is 2x times 2x to the power 1. But since you have a star here, think of this as a star. We apply the star rule from the previous section. So we get this is equal to 1 over 1 plus x squared divided by 3x minus 1 whole thing squared times, I'm applying the star rule here. 2 times your star 1 plus x squared divided by 3x minus 1 to the power 1 times the derivative of your star. Your star is this expression. Okay. If someone does not remember, please go back to section 2.4 and recall how to apply the star rule for an expression like this. Okay. We did an example very similar to this one, how to take the derivative of this. Okay. And then you need to multiply this by the derivative of your star. In that case, your star is this expression, this inside expression. 1 plus x squared divided by 3x minus 1. Still, we are not done because I have to take the derivative of this part, right? So let's take the derivative of that part. You have 1 over 1 plus x squared divided by 3x minus 1 whole thing to the power 2 times you have 2 times 1 plus x squared divided by 3x minus 1 times finally I want to take the derivative of this expression. How do I take the derivative of that expression? Well, it is the quotient rule, right? You should have 3x minus 1 squared in the bottom. In the top, you should have the derivative of the top expression, which is 2x times your g of x. Your g of x is 3x minus 1 minus, you view this as your g of x, and this is your f of x, okay? And apply the quotient rule given here. Minus, you leave your top function fixed, 1 plus x squared, and take the derivative of the bottom function, which is 3x minus 1. The derivative of 3x minus 1 is just 3. This is the derivative. Now you are done. Okay, this is the derivative. This complicated expression is the derivative of the given function. Okay, if you want, of course, you can simplify this top. You can leave the answer as it is unless you are asked to simplify. Okay. All right, let's move on. Next, I want to go over this particular example. Find the derivative of this given function. Okay. Of course, if you are trying to find the derivative of this function using the quotient rule, you will see that it's going to be very hard. Okay. Computation is very hard. So we use some sort of a strategy to take the derivative of this type of complicated expression. Okay. So first of all, let me take this f of x to be y. Okay. Then I have to find dy over dx, right? The derivative of f of x means dy over dx if I take this to be y. Okay. So my goal is to find dy over dx. How do you find the dy over dx for this function? Well, that's where the logarithmic functions are going to help you. The derivatives of logarithmic functions are going to help you. Okay. Yeah, I will copy that over here. Y is equal to, this is my function. Now what I'm going to do is, I am going to take the logarithm of both sides. Okay, logarithm of the left-hand side, ln absolute value of y, and ln absolute value of your right-hand side. I take the absolute value to make sure that this, whatever I get as the input for logarithm is positive. Okay. All right. So now what I'm going to do is I'm going to use some simple logarithmic rules. As you can see, this is a quotient, right? This function divided by this function. So you can apply the difference rule for logarithm. So this thing should be equal to ln of the top function minus the ln of the bottom function. That is one of the logarithmic rules that you learn in your pre-calculus class. Next thing I'm going to do is I'm going to pull the powers to the front. That means if you have ln x to the power r, I can pull this power r to the front. Okay, ln x to the power r is same as r times ln x. So here notice that x square root of x means x to the power 1/2. I can pull that 1/2 to the front. That's when I get 1/2 times ln x. Here also, I'm pulling this power to the front. You get 3 times ln absolute value of x squared plus 1. Here, you don't really have to put the absolute value because you know that this is plus, but to be consistent, I will put it, okay? Nothing wrong putting there. And then minus, I'm going to distribute this negative sign inside the parentheses. And then this becomes minus again. But here notice that I pull this power to the front again. Okay, that's how you get this 2 here. This minus sign is because of this minus sign. Okay, now I'm ready to take the derivative of this equation. Okay, I take the derivative of this, both sides of this equation. I'm going to differentiate my left-hand side. If I differentiate my left-hand side with respect to x, what would I get? Notice that this is not x. If this was x, I know the formula. The derivative of ln of x is just 1 over x. But unfortunately, this is not x. So I have to go with the star rule, right? Think of this as your star. Then the derivative of your left-hand side would be 1 over star times the derivative of the star. You pay the penalty. Okay, and then let's take the derivative of this right-hand side. This is 1/2 times the derivative of ln x is just 1 over x. Here again, you need to take the derivative of this expression, that is 3 times the derivative of this expression. Notice that here again you are going to apply the star rule. Okay, you have a star here. Derivative of ln of star is 1 over x squared plus 1 times the derivative of x squared plus 1. Your x squared plus 1 is your star in this case. Okay, and then similarly you take the derivative of this one. It is 1 over your star. Your star is x plus 2 in this case, times the derivative of your star, d over dx, x plus 2. Finally, you have this piece, that is minus 2 times 1 over this your star, 1 over x minus 3 times the derivative of x minus 3. Okay, now it's all about simplifying your right-hand side. Okay, so if you simplify your right-hand side, this is 1 over 2x. And of course, you can take the derivative of this expression, that is 2x. You have 2x here. You multiply this 3 with this, you get 3 over x squared plus 1 times 2x. Similarly, you can find the derivative of this one and multiply that with this one. Then you get these two expressions. Okay. Now we can simplify this right-hand side a little bit further. This becomes 1 over 2x itself, nothing to simplify there. If you multiply these two, you get 6x over x squared plus 1. Here you get minus 1 over x plus 2, and then minus 2 over x minus 3. And at the same time, notice that you had y in the bottom of the left-hand side. I multiplied both sides by y. If I multiply both sides by y, this y and this y will be cancelled. You get y prime is equal to y times this whole expression. That's why you have y here, y times the whole expression that you had in the right hand. Okay. But what is your y? Your y is this expression. You put that here to get the final answer. Okay. So your derivative y prime is equal to this function times this function. Y prime is nothing but the derivative of the function. That's what you wanted to find. Okay. Okay. That concludes that example. Here is how you apply logarithm, differentiation of logarithmic functions to differentiate more complicated functions. Okay, the next example I want to work on is this example. Use logarithmic differentiation to find x squared minus the derivative of x squared minus 3 to the power x. Notice that you cannot apply the chain rule straight away here because this power is not a constant. Of course, if this power is a constant, you can apply the star rule. Okay. But since it is not a constant, we need to use some sort of a strategy. Okay. So I will take, this is what I want to find the derivative for, right? So I'll take this function to be y. I'll take, let y is equal to x squared minus 3 whole thing to the power x. At the end of the day, I want to find y prime. Okay, that's what I want. So the trick is to take ln of both sides. Ln of y, you usually put the absolute value to make sure that you have a positive number as an input for logarithm, equal to, you take the logarithm of both sides. Okay, x squared minus 3 to the power x. I just took the logarithm of this equation, both sides. Okay, logarithm of both sides of this equation. And now what I'm going to do is I'm going to pull this power to the front. That's where the logarithm is going to help you modify this equation. This was the problem, right? Here you cannot take the derivative because you have this x as the power. Now by using logarithmic rule, you can pull this to the front. Then you get x times of x squared minus 3. Now I'm going to take the derivative of this both sides of the equation with respect to x. Okay, if I take the derivative of the left hand side, you get, by the way, you have this absolute value here. The derivative of the left hand side would be 1 over y times y prime. Notice that you have a star here. This is not x. That means it is a star. So the derivative of ln of absolute value of a star is 1 over star times the derivative of the star. This is equal to, and now I'm going to take the derivative of my right hand side. So I'm going to apply, here I'm going to have to apply the product rule. You have the product of two functions. Okay, so take the derivative of the first function, which is 1, times, leave the second function fixed, and then plus leave the first function fixed and take the derivative of the second function. The derivative of the second function is 1 over x squared minus 3. Notice that the second function is ln of absolute value of x squared minus 3. And now you need to view this as your star. Okay, the derivative of ln star is 1 over star times the derivative of the star. Derivative of the star is just 2x, because the derivative of x squared minus 3 is 2x. Now, to find y prime, I'm going to multiply both sides of the equation by y. You have y times ln x squared minus 3, absolute value of that, of course, 2x squared divided by x squared minus 3. Now, finally, you can replace your y by this expression. This is your y. So you get x squared minus 3 to the power x times ln x squared minus 3 plus 2x squared divided by x squared minus 3. Okay, that is your derivative, y prime. Okay. All right, let's move on to the next example. Here is the next example I want to work on. Okay, find the derivative of the piecewise function defined here. Okay, so you need to find the derivative. First of all, notice that this function is continuous everywhere. Okay, it is clearly continuous when x is strictly greater than 0, and it is also continuous when x is strictly bigger than 0. The question is whether my function is continuous at x is equal to 0. It is clearly continuous because if you compute the left and right limits as x approaches to 0 from the left hand side, your f of x is equal to 1. It's clear. You plug in 0 here, right? Find the left limit, and then to find the right limit, as x approaches to 0 from the right hand side, you plug in 0 in this function. Again, you get 1. And of course, your function value at 0 is also 1 because you plug in 0 in this function to find the function value at x is equal to 0. As you can see, all these values are equal. So f is continuous at x is equal to 0. Okay, continuity is not a problem. Okay, so we need to find the derivative. Let's try to find the derivative. Clearly, the derivative I denote it by f prime of x is equal to, I can find a piecewise function for my derivative. Okay, First, I'm going to find the derivative when x is strictly less than 0. My function is e to the power x. The derivative of e to the power x is e to the power x itself. That is valid when x is strictly less than 0. And then I also can find the derivative of my function f of x when x is strictly bigger than 0. Okay, when x is strictly bigger than 0, I can find the derivative. What is the derivative of e to the power minus x? The derivative of e to the power minus x, you need to apply the star rule here again. Okay, this is your star, e to the power star. So if you differentiate that, you get e to the power star times the derivative of the star. The derivative of the star is minus 1. Now, what happens when x is equal to 0? I have a derivative formula as a piecewise function. What happens when x is equal to 0? What happens to the derivative when x is equal to 0? For that, I'm going to take g of x as this function, e to the power x, and h of x as the function in the right-hand side. Pardon me, I'm going to take g of x as this function, e to the power x, and then h of x as this function, minus e to the power minus x. Now I'm going to find the left and right derivative. To find the left derivative, I'm going to have to plug in x is equal to 0 in this function. That means I plug in g of 0. That is my left derivative, which is equal to 1. Clearly, if you plug in x is plug in the derivative, plug in 0 in this function, h of x. H of 0 is equal to, it is minus. As you can see, the left derivative and right derivative, they are not equal. So the function is not differentiable at x is equal to 0. F is not differentiable at x is equal to 0. Okay, so in this piecewise formula, I have to write undefined. Derivative is undefined when x is equal to 0. This is the derivative formula for the given piecewise function. The derivative is e to the power x when x is strictly less than 0. The derivative is undefined when x is equal to 0. And the derivative is minus e times e to the power minus x when x is strictly greater than 0. Okay, so that completes that example. With that, we conclude section 2.5. I'll stop there. I'll see you next time.